inverter. And as you have already seen in power electronics class, you have studied two modes of operation of three-phase PSI, and that is 180-degree mode and 120-degree mode. So in 180-degree mode, each thyristor conducts for 120 degrees. Sorry, 180 degrees. In 180-degree mode, each thyristor conducts for 180 degrees. And in 120-degree mode, each thyristor conducts for 120 degrees. Now we will see the waveforms of a 180-degree mode of operation. And here, the thyristors, as I already said, each thyristor conducts for 180 degrees. And firing sequence is in such a way that after each 60-degree interval, next thyristor fires. That means if T1 is fired first, and after 60 degrees, T2 is fired, and after another 60 degrees, T3 fired, and so on up to T6. Now we will see how this devices are fired. So here we can see that T1 is fired for 180 degrees, and similarly T3, each thyristor fired for 180 degrees in 180 mode. And suppose if you are considering the first interval, that is from 0 to 60 degrees, we can see that the devices conducting are T1, T6 and T5. Okay, so we will write the devices conducting like this, 5, 6, 1. Okay, and next interval from 60 to 120 interval, the devices conducting are T1, T6, T2. T2 starts from this point, so it is 6, 1, 2. So from this sequence, we can see that without looking into this part, this diagram, you can directly write the sequence like 5, 6, 1. Just remove 5 here. So next step is add the next thyristor, that is 6, 1, 2. Then remove T6 and add 3, T3. So 1, 2, 3. In this manner also, you can find out what are the devices conducting in different intervals in an easy way. Okay, now we can see how the voltage waveforms are appearing. And these voltage waveforms are phase voltages. We will see first how the waveforms, phase voltage waveforms appear. And here, as I said earlier, it is having 3 limbs, A, B, C limbs. So I am taking the voltage from V, A, that is reference is taken as this negative part, this lower part. So we will see VAO. So here, this is the output waveform, voltage phase voltage waveform from a variable, from a voltage source inverter. And here we can see that the output voltage is varied from Vs by 3, then increases to 2 Vs by 3, then Vs by 3, then minus Vs by 3, minus 2 Vs by 3, minus Vs by 3, and so on. So this completes one cycle of operation. So this process repeats. This completes one cycle of operation, that is in 360 degrees, we'll get one cycle. The value of Vs by 3, 2 Vs by 3, etc. that you have already studied in the power electronics class with equivalent circuits. So I am not going into the details of that. So then similarly, you can take the voltage from the other limbs also, VBO and VCO. That is, these are out of phase by 120 degrees. You can just draw like this. So this is started at this point. So after 60, then another 120 degrees, this cycle, this VBO cycle starts from here. And after, and similarly, you will get the C phase voltage. So that is VCO. So after this point, after 120 degrees, the next cycle starts. Next wave will be C voltage starts. And these voltages are given to the stator of this induction motor. Okay, and coming to, and this is the phase voltage waveforms. And if you're looking into the voltage waveform of line voltage waveform, you can see that what is the line voltage, and if you're getting the phase voltage here, you will get VAB is the line voltage, and which is given to the windings A and B, stator windings of this induction motor. So if you know VAO and VBO, you are able to find the line voltage VAB as VAO minus VBO. So simply directly subtract this VAO minus VBO. So from this waveform itself, you can subtract, you can see that VAO is Vs by 3 minus VBO is minus 2Vs by 3. So you will get Vs by 3 plus 2Vs by 3, so which is equal to 3Vs by 3 is equal to Vs. So in this interval, you got the line voltage waveform. These are the line voltage waveforms of 180-degree mode of operation of VSI. So you got in this interval the voltage as Vs by 3, and just you can check the next interval also. And here the voltage VAO is 2 Vs by 3 minus, this is minus Vs by 3, then 2 Vs by 3 minus of minus Vs by 3, you will get it as Vs 3 Vs by 3, so which is also equal to Vs. Okay, so this interval also the voltage is Vs, right? And similarly, you can find out the differences in all the intervals. And from 120 to 180 degrees, the voltage is 0 and then minus Vs. So this is the pattern of the line voltage following line voltage that is applied to the induction motor. Okay, and similarly, you can find the other line voltages also, that is VBC. You will obtain VBC as VBO minus VCO, and similarly VCA, VCO minus VAO. And otherwise also, if you go the voltage wave from VAB, you can just get the other voltages by simply giving a phase shift of 120 degrees. That means after 120 degrees, this wave shape starts, and after another 120 degrees, this wave starts. Okay, now so this voltage we are obtaining from a variable source, variable output of mode as this. So this is because since the output voltage according to it, but this, so this comes as this is looking for 180 degrees. Frequency can be controlled. So we have each thyristor T1 to T6 conducts for 180 degrees. And if you're able to turn off this, we'll be able to vary the frequency. For example, if the on period of the switch is 10 milliseconds, then the fundamental time period is to 60 degrees. So fundamental time period will be 20 milliseconds. So what is the frequency then? The frequency is 1 by 20 milliseconds, which is equal to 50 hertz. Okay. And if you want to change the frequency, if you want to double the frequency of this, then what you will do, you will change the switch on time. We will change the switch on time of the switches and let it be 5 milliseconds. If it is 5 milliseconds, the fundamental period becomes 10 milliseconds. So what is it? 100 hertz. So in this way, by varying the switch on period of this frequency, and varying the frequency alone may cause problems when it is operated in below the rated speed. You already seen in the previous modules that you can operate the induction motor synchronous operating at below the synchronous speed. You constant torque mode. That means you need to fix the V by F ratio constant. That means it's done by controlling the turn-on period of the switches in the inverter. And for controlling the voltage, you can control it by varying the input voltage. Okay. So in this session, so VSI connected drive, as we know, in stepped wave VSI fight induction motor drive has number of drawbacks because the waveform is like stepped wave. So from this, it's evident that the harmonic content is large low frequency harmonic content. So this increases motor losses and thus the efficiency, and this causes derating of the motor. So motor produces pulsating torque due to this harmonics, and also in three-phase triple harmonics will be absent, and at low speeds harmonic content increases. So machine saturates at low speeds due to high V by F ratio. That means V by F ratio, if we low speeds means for low speeds we need to reduce the frequency. Speed is directly proportional to frequency. So for low speed you need to reduce the frequency. That means this V by F, if you are not varying the voltage, the V by F ratio will be increased. So what happens, and this as actually flux is proportional to V by F, so flux will increase, though there is a chance for saturation. So due to this effects, it overheats the machine at low speeds. Machine at low speeds. Okay, so this is the first session. So here we have seen a variable a voltage source, inverter, feeding, and three-phase induction motor, in which we are using a stepped wave inverter output voltage waveform, and it is having number of drawbacks as mentioned here. So this is the first session, and in the next session we will see the PWM, and in which that these drawbacks can be rectified. So this is the end of the first session.
Okay, ma'am. So we have the first 20 minutes. So we have got a few questions from the students. So we have got a question from Hafiz Mohammed. So he's asking if the frequency is 1 by T, then how it is doubled by varying the time period?
Actually, as I said, time period of, see, in 180-degree mode of operation, each thyroid conducts for 180 degrees. In the other 180 degrees, switch will be off. One cycle plus 360 degrees. So a thyristor conducts for 180 degree means that is the on period of that particular switch. So off period, the total time period is 360. That means time period. So it will be, if it is 10 milliseconds, the total time period T is 20 milliseconds. So it will be 1 by T's frequency. So you will get frequency like that.
Okay, ma'am. So if that is answered, so to the students, actually, you can actually post your queries using the Q&A button, which you can find in the dashboard below the screen, actually. So we have got another question as well, ma'am. So that is from Anjali Jayachandran, which is, she's asked, do we always need to keep the V by F constant, or only when under the synchronous speed? She's asked, do we always need to keep the V by F, that particular thing, as constant, or only when under the synchronous speed?
So usually, if there are two modes of operation, one is below base speed, in which we usually use variable voltage methods, etc. Variable voltage, variable frequency control. Below rated speed only, we are able to vary voltage, armature voltage. And above the rated value, above the rated speed, we cannot vary the rated voltage above the rated value. So below the rated region, we will be keeping V by F ratio constant. That means V by F is directly proportional to the flex. So flex, we are maintaining the flex constant. In the above phase speed region, what happens is that that is V by F, we are not able to change the voltage above the rated voltage. So what happens when, if we want to increase the speed above the rated speed, we need to increase the frequency. Since V by F, like phi is proportional V by F, when if we want to increase the speed, we need to increase the frequency. But we are not able to change.
Ma'am, sorry to interrupt.
Hello?
Madam, sorry to interrupt. Actually, ഇപ്പോൾ കുറച്ച് മുന്നേ പറഞ്ഞ ഓഡിയോ ഒന്ന് ക്ലിയർ അല്ലായിരുന്നു മാം. സോ ക്യാൻ യു പ്ലീസ് റിപ്പീറ്റ് ദാറ്റ് ആൻഡ് ഇഫ് യു ക്യാൻ ഗിവ് an explanation in Malayalam as well, because some students have requested for it.
Hello?
മാഡം, തൊട്ടു മുന്നേ പറഞ്ഞത് ക്ലിയർ ആയില്ല. മാഡം, അതൊന്ന് മലയാളത്തിലും കൂടെ ഒന്ന് എക്സ്പ്ലെയിൻ ചെയ്ത് കൊടുക്കാൻ പറ്റുമെന്ന് കുറച്ച് പേര് നമ്മുടെ അടുത്ത് റിക്വസ്റ്റ് ചെയ്തിട്ടുണ്ട്. ഇതേ ക്വസ്റ്റ്യൻ തന്നെ, ഈ ഇപ്പൊ ചോദിച്ച അതേ ക്വസ്റ്റ്യൻ തന്നെ ഒന്ന് മലയാളത്തിലും കൂടെ ഒന്ന് എക്സ്പ്ലെയിൻ ചെയ്യാമെന്ന് ചോദിച്ചു.
അതായത് നമ്മള് ബേസ് സ്പീഡിന് താഴെയാണെങ്കിൽ നമ്മൾ വോൾട്ടേജ് V by F കൺട്രോൾ യൂഷ്വലി ഇപ്പൊ ഫസ്റ്റ് മൊഡ്യൂൾ വെച്ച് അല്ലെങ്കിൽ സെക്കൻഡ് പല പ്രീവിയസ് മൊഡ്യൂൾസ് ഒക്കെ പഠിക്കുമ്പോഴും നമ്മൾ രണ്ട് റീജിയൻസ് പഠിക്കുന്നു. എബോവ് ബേസ് സ്പീഡിൽ പ്ലസ് ഫ്ലെക്സ് വീക്കനിങ് മോഡ് എന്ന് പറയും. എബോവ് ബേസ് സ്പീഡിൽ ഫീൽഡ് കൺട്രോൾ ചെയ്യാൻ വേണ്ടിയിട്ട് വി ബി യൂസിങ് ഫ്ലെക്സ് വീക്കനിങ് മോഡ്. ദാറ്റ് മീൻസ് എബോവ് ബേസ് സ്പീഡ് വരുമ്പോൾ, എബോവ് ബേസ് സ്പീഡ് മീൻസ് റേറ്റഡ് സ്പീഡ്, എബോവ് റേറ്റഡ് സ്പീഡ് വരുന്ന സമയത്ത് നമുക്ക് വോൾട്ടേജ് ഇൻക്രീസ് ചെയ്യാൻ പറ്റില്ല. റേറ്റഡ് വോൾട്ടേജിനേക്കാൾ കൂടുതൽ റേറ്റഡ് വോൾട്ടേജ് കൊടുക്കാൻ പറ്റില്ല, റേറ്റഡ് വോൾട്ടേജ് കൊടുക്കാൻ പറ്റുള്ളൂ. ആ സമയത്ത് നമുക്ക് സ്പീഡ് ഇൻക്രീസ് ചെയ്യണമെങ്കിൽ നമ്മൾ ഫ്രീക്വൻസി ഇൻക്രീസ് ചെയ്യും. ഫ്രീക്വൻസി ഇൻക്രീസ് ചെയ്യുമ്പോൾ സ്പീഡ് ഇൻക്രീസ് ചെയ്യും. അപ്പൊ V by F എന്ന് പറയുന്ന ഫ്ലെക്സ് കുറയും. ദാറ്റ് മീൻസ് ഫ്ലെക്സ് വീക്കൻ ചെയ്യും. ദാറ്റ് ഈസ് ഇൻ ദ ഫ്ലെക്സ് വീക്കനിങ് മോഡ് എബോവ് ദ ബേസ് സ്പീഡ്. ബിലോ ദ ബേസ് സ്പീഡിലാണെങ്കിൽ അത് നമ്മൾ ആ ഫസ്റ്റ് മൊഡ്യൂൾ തന്നെ ഒരു ഇക്വേഷൻ, ഒരു ഡയഗ്രാം ഒക്കെ വരച്ചിട്ട് തന്നെ നമ്മൾ എക്സ്പ്ലെയിൻ ചെയ്യുന്ന ഇതാണ്. ബിലോ ദ ബേസ് സ്പീഡ് വരുമ്പോഴത്തേക്കും അവിടെ നമുക്ക് വി ക്യാൻ വേരി ദ വോൾട്ടേജ് ഫ്രം 0 to rated value. അപ്പൊ 0 to rated വാല്യൂല് അവിടെ നമ്മൾ ഫ്രീക്വൻസി ഇൻക്രീസ് ചെയ്യുമ്പോൾ ഫ്രീക്വൻസി മാത്രം ഇൻക്രീസ് ചെയ്തു, വോൾട്ടേജ് വേരി ചെയ്തിട്ടില്ലെങ്കിൽ V by F is proportional to flex. അപ്പൊ എന്ത് ചെയ്യും, ഫ്രീക്വൻസി there is a chance of ഫ്ലെക്സ് ഇൻക്രീസ് ചെയ്യാം. ഫ്രീക്വൻസി കുറച്ച് സ്പീഡ് കുറയ്ക്കുകയാണെങ്കിൽ അവിടെ ഫ്ലെക്സ് ഇൻക്രീസ് ചെയ്ത് സാച്ചുറേഷനിലേക്ക് പോകാനുള്ള ചാൻസ് ഉണ്ട്. യൂഷ്വലി ആ റീജിയനിൽ will keep V by F ratio constant. Okay, hope it is clear.
ഓക്കെ മാഡം, ആക്ച്വലി നെക്സ്റ്റ് ഒരു ക്വസ്റ്റ്യൻ, രണ്ടു മൂന്ന് ക്വസ്റ്റ്യൻ ആണ് പെട്ടെന്ന് ചോദിക്കാം മാം. അതില് ഒരു ക്വസ്റ്റ്യൻ വെച്ചാൽ VSI ഡ്രൈവ്സിന്റെ മാക്സിമം പോസിബിൾ ഫ്രീക്വൻസി എത്രയാണെന്നാണ് ചോദിക്കുന്നത്. വാട്ട് ഇസ് ദ മാക്സിമം പോസിബിൾ ഫ്രീക്വൻസി യൂസിങ് VSI ഡ്രൈവ്സ്? Alex,
so in maximum possible frequency in the variable. So here we can see that we will be using different devices in this. So about frequency, there is range, pala range depends upon the application. But T1 എന്ന് പറയുന്ന thyristor ആണെങ്കിൽ thyristorന്റെ നമ്മൾ usually thyristor switches are used for low frequency application, high power low frequency applications ആണ്. അപ്പൊ അതേ so thyristors low frequency application, high power application will use thyristors. അപ്പോൾ ഈ സ്വിച്ചസിന്റെ അതിനനുസരിച്ചിട്ട് നമുക്ക് ഫ്രീക്വൻസി പിന്നെ അതേപോലെ മോസ്ഫെറ്റ് യൂസ് ഇൻസ്റ്റെഡ് ഓഫ് ദിസ് സ്വിച്ചസ് മോസ്ഫെറ്റ് യൂസ് ചെയ്യാം. ആൻഡ് വി കൻ യൂസ് IGBT ട്രാൻസിസ്റ്റേഴ്സ്. അപ്പോൾ സ്വിച്ചസിന് നമ്മൾ ഹൈ ഫ്രീക്വൻസി ആപ്ലിക്കേഷൻസ് വരുന്ന സമയത്ത് നമുക്ക് വെരി ഹൈ ഫ്രീക്വൻസി മെഗാ ഹെഡ്സിലും ഒക്കെ കിലോ ഹെഡ്സിലൊക്കെ യൂസ് ചെയ്യാൻ പറ്റും.
Okay. Okay, ma'am. Thank you. നമുക്ക് ഒരു 2 ക്വസ്റ്റ്യൻ എടുത്തിട്ട് നമുക്ക് അടുത്ത സെഷനിലോട്ട് പോകാം മാം. അതായത് ഇതിനകത്ത് യൂസ് ചെയ്തിരിക്കുന്ന ടൈപ്പ് ഓഫ് കൺട്രോൾ റെക്ടിഫയർ ഏതാണെന്നാണ് ഒരാളുടെ ചോദ്യം.
Controlled rectifier. That means in this, suppose I will show you
ഇതിൽ യൂസ് ചെയ്തിരിക്കുന്ന ഏത് ടൈപ്പ് ആണെന്നാണ് ചോദിച്ചത്.
This block, like a controlled rectifier means that is a fully controlled rectifier. So this can be, so here if you want to vary the input voltage, if this input voltage vary, we are using a controlled rectifier. You can use fully controlled rectifier here.
Okay, ma'am. Okay, ma'am. അതുപോലെ വേറെ ക്വസ്റ്റ്യൻ ചോദിച്ചിരിക്കുന്നത് ഫസ്റ്റ് ഗ്രാഫിനെ കുറിച്ചാണ് ചോദിച്ചിരിക്കുന്നത്. അതിൽ 2/3 VS എന്ന് പറയുന്ന ആ ഒരു ഇക്വേഷൻ എങ്ങനെയാണ് കിട്ടിയതാണ് ചോദിച്ചിരിക്കുന്നത്.
2 VS/3. Okay, that is
VS/3.
And actually this requires a detailed section. Even then I will just inform, because in the power electronic class we are finding this voltage with the equivalent circuit. Actually this VA, this voltage VA, VB, VC, from this we are giving this input to the stator of the induction motor. That means, and for finding this stator windings are star connected. So in each interval we can see that thyristor, either top thyristor, in each interval either T1, one thyristor from top group and 2 thyristors from bottom group will be conducting, or 2 thyristors from top group and 1 thyristor from lower group will be conducting. So if, by considering the turn on of the switch, suppose in the first interval T1, T6, T5, if you're turning on T1, if you're turning on T1, we can see that the voltage coming this side is VS. VS is coming to this side. And if lower voltage, this is connected, VA as 0. So in this way, you can draw the equivalent circuit by considering the stator voltages. Star connected stator voltage, like you can connect this DC input voltage. Then the easy method is that if you are finding T1, T6, T5, then there will be 2 thyristors, two positive thyristors, that is T1 and T5. T1 and T5 from the positive group and T6 from the negative group. That means the complete VS voltage is giving to this equivalent circuit. So the top, if 2 top thyristors T1 and T5 are connected to the top plus side of this, see T1 and T5, say this is T5, these are connected to the positive side of this DC side, and the negative side of the DC side is connected with the bottom thyristor T6. But T6 means that is B. T1 and T5 are A and C. So A and C voltages VAO and VCO voltages will be VS/3, VS/3 and VS/3, minus this V, the bottom switch which is connected to the negative side of the supply is minus 2 VS/3. Minus 2 VS/3. So by totally adding these voltages, you will get. So similarly here 612 period. Here we can see that 2 bottom thyristors. 2 bottom thyristors, that means even thyristors 6 and 2. So 6 and 2 you will get minus V/3, minus V/3. Then T1 as 2 VS/3. The limb which is connected to the which is connecting only one thyristor is having 2 VS/3, other is having VS/3. So actually this need a detailed description with the tables and equivalent circuit of each interval. So it will be very easy to understand, but that much time it is there. You can refer either Nagmohan or Duque or the power electronics. Any of the power electronics textbooks will be giving a clear explanation of the derivation of these voltages from equivalent circuit.
Okay, ma'am. Ma'am, thank you, ma'am. Questions session. Probably you can continue with the second lecturing session, ma'am.
Okay.
And questions session address.
Okay.
Thank you. Ma'am, okay, we can continue with the next session, ma'am.
Okay. And we'll start the next session. That is the Sine PWM inverter fed induction motor. And we have already seen the drawbacks of the previous square wave inverter output system. We are Sci-Fed system, and now we will see, and these drawbacks can be overcome by using a PWM inverter. So in PWM inverter, see here, this is the circuit block diagram setup in which the input supply is AC and we are feeding the voltage through a diode bridge. Unlike in the previous case, we are using a control rectifier. Control rectifier, that means there you need to vary the input voltage. And this is given through the filter to the PWM inverter. And here in PWM inverter, this PWM inverter itself is giving a variable voltage, variable frequency output to the induction motor. In the previous case, in the square wave inverter type, we have seen that the variable frequency can be varied by controlling the turn on of switches, and for varying the input voltage, varying the output of the VSI, we need to vary the input voltage. Unlike this, in PWM inverter, we need to control. We will get the output of the PWM inverter itself as a variable voltage, variable frequency output, so that you can directly give to the stator of the induction motor. That is the advantage with the PWM inverter setup. And now we will see the same circuit diagram can be used for this PWM inverter also. Inverter setup is same, like 6 switches, positive switches, positive group switches, and negative group switches. Here just shown a circuit diagram which uses a transistor. In the previous case, we have used a thyristor, and these switches can be anyone depending upon the application. As in the question, one question asked, how the frequency maximum limit, and this can be determined by this. So according to the application, you can select the switches. In here, this diagram shows a transistor switches. Okay, this can be either IGBT, MOSFET, JCR, etc. And here we can see the output voltage waveform from the PWM inverter setup. And here these are PWM means pulse width modulation inverter. So these are the PWM pulses. So fundamental output voltage in this case will be sinusoidal waveform. So in order to, we have seen PWM in different, so when you are doing the project and when you are studying different at the application level also, PWM. And what is actually the concept behind the PWM? This is a final output voltage, and I will show you how these voltages are coming from the PWM. So this is a sinusoidal PWM inverter for induction motor control. And here we can see PWM is just a comparator. So here, see, this is a block diagram showing the PWM operation in which we are giving two waveforms, two waves to the comparator. This is comparing a triangular wave with a control wave. This wave, you can call it as a reference wave or control wave. And here our control wave is a sine wave. Okay, here the control wave is a sine wave. And how you are selecting the output voltage at the some fundamental output voltage, then you will select your control wave or reference wave is sinusoidal wave. If So this control wave, output of the comparators given here in this case, we get to this, which is transistor switches for controlling the difference. And we will show you with this waveforms how this controlling. As here, see, we can have two waveforms. These two waveforms are giving the first wave as high frequency carrier wave. Is a sinusoidal waveform, that is our control wave. See, and here, this is our control wave, or we can call it as reference wave. And here we can see as more than the magnitude of the control wave or the reference wave is more than the trend pulse plus VDC. And from this point, the okay. So in this having more positive values, this part is having more. So this is the concept behind the PWM. So when you are forms triangular wave and things will be okay, inverter. So when you're considering the, hello,
ma'am, I just remember. If it's possible.
actually,
thank you.
PWM inverter applications learning, we will see the PWM. അപ്പോൾ ഈ രണ്ട് ഇൻപുട്ടും കൂടെ കമ്പയർ ചെയ്യുന്നതാണ് ആക്ച്വലി given to this നമുക്ക് ഫോർമുല we can see ഇവിടെ ഒരു ട്രയാങ്കുലർ വേവ് എന്ന് പറയുന്നത് ഈ ട്രയാങ്കുലർ വേവ് എന്ന് പറയും. വേവ് സൈൻ വേവ് കമ്പയർ ചെയ്യുമ്പോൾ അതിന്റെ ഇവിടെ this will get a plus VD output. Plus VD output. എന്ന് പറഞ്ഞാൽ ഈ തൈറിസ്റ്റർ ഈ അല്ലെങ്കിൽ ഇതിപ്പോ ഞാൻ ഈ ഇൻഡക്ഷൻ മോട്ടറിന്റെ പാർട്ടിലേക്ക് പോയിട്ടില്ല. അതിന് മുമ്പ് തന്നെ ജസ്റ്റ് ഒരു ലിംബ് കൺസിഡർ ചെയ്യുകയാണെങ്കിൽ ആ ലിംബിൽ എങ്ങനെ ഓപ്പറേറ്റ് ചെയ്യുന്നു എന്നുള്ളതാണ്. അവിടെയുള്ള തൈറിസ്റ്റർ ഓൺ ആവും അല്ലെങ്കിൽ സി വിൽ ഗെറ്റ് പ്ലസ് സി